Okay, so I've brought up the factors that I had before for pizza. And so in this case, I'm a bit more naive about what time and temperature might do to my process. So I go to custom design, I'll load the factors in, and I'm going to leave them all as easy to change. And I'm just going to make my response surface design for this, which means we're going over the full range of time and temperature, not cutting off the high-high combination or the low-low combination. And I'm just going to make it 24 runs to have it be a nice round number. And I'll click Make Design. So this is just a response surface design in these 4 factors. We've got 3 different types. And we'll make the table. And okay, so now if I were to make a graph of these points with time and temperature, okay, here's where, when I highlight the points in the lower left corner, you'll see it says 3 rows are selected. So it's a little information there, you know, in this graph. And then if I hold my control key and I select the upper right corner, and it says 6 rows have now been selected. So out of my 24 trial design, 6 of them were at either the high-high or the low-low. And now I go to do whatever response measurement it is. Maybe it's the texture of the crust. And unfortunately, one of them is just goo because the dough hasn't cooked, and the other is ash because I've totally toasted it. And texture really doesn't mean very much. Or taste. Do you want to eat raw dough or ash? Or, you know, so the point is, you can think of, this could happen in lots of different processes. So if I take those selected rows, and I'll go back to my data table, they've been selected here, I'm going to hide and exclude them. So in other words, I'm going to say that, you know, there's, I've lost 1/4 of the experiment. And if I just put some data in over here, so I'm just going to throw in some random data here. So let's just make it random integers. Okay, so I just made up the data. But now I go to fit my model. And remember, the model for this was the full RSM. There's a chance this might not fit. It might, but let's just run it. And it says, you know, there's a singularity here. That I lost enough information to fit the full model that was proposed. I mean, very often you'll find with a designed experiment, losing 1, 2, maybe even 3, usually your model will still run. However, if you've got a squared term and you lose all the middles, it'll never run. If you have a particular interaction and you sort of get yourself so that all that's left is a diagonal in those 2 factors, there's no way to fit the interaction. So the point here is this model is not going to work. So what we're going to do is go to DOE, and in this case we'll pick Augment Design. And so we'll take the factors that worked and keep those. But now when we do the augmentation, we want to add in the constraints. So once again, I'll specify some linear constraints here, and I'm going to add the 2. One was for the high. I'll just use the 600 this time, and the 500 here. I need to flip that inequality. So this is now saying add on to the existing trials that worked, but don't pick anything in the upper right or the lower left corner of the time temperature part of the space. And if I just clicked augment now, you know, if this all happened on the same day, maybe you wouldn't be worried. But what if this is now it's a day later, a week later, you're coming back? It's usually a good idea to add a blocking variable because the process has shifted in time here, and I want to know if the 2 groups of data are, you know, distinctly different from each other. So I'm going to click add a new blocking factor. Okay? And now when I go to augment, it'll say how many trials, and by default, the algorithm will put in 8 more than the ones that worked. So you can see it said counting the 18, it's defaulting to 26. You know, if you wanted to be on the safe side, you might want to bump that up to 30. You know, this is now your choice. I'm going to do 12 more experiments. You know, this is now a day later. Maybe that's a reasonable amount. So I'll click Make Design. And here we go. And so we'll click Make Table. And now, you know, I'm going to take the first ones and make those green. Maybe make them circles. And oops. Did I just delete them? Yep. Control Z will back you up. Didn't mean to. I was going to this one here, invert. And then I'm just going to make these, say, diamonds. And we'll make them red. Okay, so now, the only thing I am concerned about here, okay, I'm going to just go with this, and let's go to Graph It. So if I go to Graph Builder, which is the easy one to do, I can say time here and temperature here. And get rid of that smoother. You can see where the original points were, and what's happening here is there are red diamonds on top of green circles. Okay, so I mean I can sort of see that right over there. And notice when I highlighted it says 2 rows are selected. But what I want you to see is it has added trials in. You can also, if you want to see a little bit more in higher dimension, you might say, let's do a scatter plot 3D of time, temperature, and size, and let's do it by pizza type, which means it'll give me 3 different cubes, one for cheese, veggie, and meat, and I might want to color by block, and we'll click OK. And here you can see I can make those markers bigger. Some point done there. So this is just the cheese data, but if I look at the time temperature, like straight down on it, you can see we avoid the high and low combinations. But if you look at it sort of this way, we can do the same for all of these. The time temperature, it honored those constraints, and you can see it's filled out more regions of the design space. So, you know, that required some subject matter expertise. Where'd the constraints come from? You know, you don't just make them up. You sit and talk about it and you say, you know, I think we can go this far before it burns, or we can go this far, you know, and it'll still cook. Okay, so that, you know, and you can try it and sometimes you're wrong and you might have to augment it again. But the whole idea is we don't take the first 18 trials and say, got to throw them away. That design broke, we can't use it. You're able to salvage those original 18 that worked. Okay, so that was pretty quick. I think what I'm going to, any questions on that? Yeah?
You picked the number 12, but is there any way for the system to show you the minimum number of runs you need to add in order to get the model viable again?
Well, it would have by default gone to 8. I probably could have cut it down to 4. Let me try that. So if we go back to this point, I click Augment. Okay, so by default that previously had an 8 there, so it was a 26. I'm going to go to 22 because, you know, now I'm thinking, you know, this is, you know, I lost 6 points and I'm only adding 4 back. So this is already a smaller design than the original one. But at least with the time and temperature, I probably will fill in. So this might be on the minimum. So let's try it. So what I didn't check, but I'm sure would have worked with the other example, was the data for that would have worked. So here is, I guess this is the design that it made. Wait a minute, that's the original design, right? No, I have to make the table. That's what I didn't do. Okay. So here is the block 2, are these 4 here, and I don't have data for them yet. So I'll just make up some data here. 20, 9, 14, 6. Okay, so now I've got enough data that if I go to analyze this and I pick fit model, and it's the full quadratic model down here with the addition of the blocking factor, so that's one extra term, and we run it, it looks like it may have fit, but there's, let me look at the parameter estimates. There aren't very many degrees of freedom. Maybe I want summary. I'm looking for a good. Yeah, so the number of observations is 22. Surprised one of these doesn't have a more, let's say maybe it's a NOVA. There we go, yeah. So the number of degrees of freedom is pretty small because we didn't add that many trials to, we actually had fewer trials in the augmentation than the original design had. Okay, well that actually took us closer to lunch, but I'm still going to try to squeeze in a quick example of another augmentation. So in this case, I have a process here. This is a definitive screening design. We haven't talked about them, but it was actually one of the very first ones ever run, and it was for a process where they were trying to capture CO2, and so there are 10 factors in this. So they're labeled here A through J. I used to have the names and the actual values, but the company saw me talking about it, and they said, don't do that. Apparently it was proprietary enough. But if we were to go at the analysis of this, I'll just do a fit model here for it. So if we want to look at the yield, if I just put that in, those are the main effects. But if I put in all of this and do that macro for response surface, now for 10 factors, this is a big model. This is 60-some terms, and I've only got 24 experiments or thereabouts. So you can't do least squares, so you do something like stepwise. And I'll come in here and say use the minimum AIC. Let's plot that criterion history when we do this. And I'm just going to hit go with that. And so it comes up with this 10-term model, and we run it. And it turns out it's got all this stuff in it. And my point is that the 4 fit definitive screening came about, which is now built into JMP. If I use that, that's really the most robust way to analyze this. I fit this model with stepwise several different ways, forward, backwards. Well, you can't go backwards. But I fit all possible subsets. I mean, it did all sorts of things. And the thing was, factors A, B, and C always were important. But sometimes when you did it one way, you got factor F, was just barely significant. Did it another way, all subsets G was significant. Do it another way, D was sort of significant. So it's like 3 slam dunk in, 3 were not too clear, and the other 4 weren't important. So the solution to that was, well, why don't we take this existing design and augment it? So we'll take the original design in factors, in the 6 that we were interested in. So I'm picking a subset of the factors. I'll put the yield up here. Okay, add runs onto this existing design. And there's no constraints. And so again, you probably, anytime you do this, you want to add a block factor. The only thing now is I want to make this a full RSM in all of these factors. So when I do that, that message was just the blocking factor doesn't go in with those additional. And I'll make this 36, so I'm adding 12 onto my original 24, and I'll make the design. And while that's happening, I'll just pull up the slides that goes with this. Okay, so in this slide, you can see the black star. This is the example I just did. I took the 10-factor DSD, took the 6 that look like they could be important, but there's not enough information to fit the 6-factor quadratic. Added on enough trials to fit that full 6-factor quadratic, and it's only 2 bigger than if I knew the right 6 to begin with. So I could do this in 2 steps, okay? And that's what we just did here. So if I go back to the design that just finished, I think it's, did I lose it? Oh, make the table again. You can see that from, this is the second block, and I would need to get data for the second block. Okay, but those extra 12 runs will now fit the full 6-factor response surface when added to the original 24. So rather than starting over and doing a 34-run experiment, I just added 12 onto the original. Now, this will work if you don't change your factor ranges. If you did your screening and the result of that was, oh, we need to go higher in this factor and we need to go lower, and you change the ranges, the augmentation doesn't really work very well because you're changing the original space you're adding on to. And if you change it enough, you might as well start over from scratch. Okay? And that takes us right to noon. So if there's any questions on the fixing a broken design or design augmentation, we're happy to do more of that later. But I think we're close to where we wanted to be at this point. So I think we have lunch for 1 hour and we get going again at 1 o'clock.
Whilst you were taking a break from DOE Next Level Methods and needing lunch with colleagues and perhaps calling home to friends and family, perhaps some other questions came up. So before we get going into the afternoon, are there questions from the morning? And then 2, are there questions for Bradley Jones? And even questions out in Zoom. So don't hesitate to ask questions in chat. So we're here. And as I've mentioned, obviously this is an enormously aggressive schedule of all the material that we're going through. And we're glossing over a lot of the details kind of thing. So Tom and I will be here all week. So catch us in the hall. We'll throw up the computer and walk you through some things or whatnot. So this is, by definition has to be kind of quick, catching some of the peaks, but we don't want to leave you with any questions if we can help. So for the afternoon then, let's go through 2.0. So these are going to be other useful designs. I'll start out and I'll do some mixture models, and then Tom will do modern screening designs, but I'll maybe hit that at the end, or he can integrate that into maybe a preamble before we do mod sim kind of a thing, because I know we want to get to mod sim. So I'm going to go through these relatively quickly, and then I'll do the measurement systems analysis, and then accelerated life test and nonlinear. just in case you thought it was going to be an easy afternoon. So hopefully you all have lots of Coca-Cola products and other caffeine, tea. So off we go. So let's talk a little bit about mixture models. This is from a presentation that I gave here last year. So I'm not going to go through the whole thing again as much as pick out a few highlights and use it as an introduction to, hey, this is kind of what the world of mixture models is all about. So this, the context of this use case is that we are rapidly trying to get capability in hypersonic weapons, and they become hypersonic typically because of the fuel, and that's probably the most important part to get that right. So we've been doing a lot of work in that regard, trying to make sure that we can exceed Mach 5 using solid fuel ramjet and these type of technologies. But it all comes down to chemistry. So chemistry is mixing things together. So what we have to do is figure out what the right blends are. So in this particular case, you can't see the colors, and I need to keep that in mind, that you guys don't see everything that I see in the charts here. But this particular example had a mixture of, we probably had like 12 primary components that were in there that were being blended. And then we had 27 constraints. So this was very, it was not straightforward at all, but ultimately we ended up delivering a very useful insights to them. So what exactly is a mixture model? Well, by definition, if you have a two-component mixture, ingredient A and ingredient B, if you have to sum to 100%, then if you have 20% of A, then you're going to have 80% of B. So what you have is this red line here of what is the art of the possible for your design. So by definition, you have an inherited high collinearity. So collinearity does what for you? Does it help or hurt you? It hurts, right? And it can hurt pretty bad. Multicollinearity is one of those bad things that can happen to you, and it is detected by what's called VIFs, variance inflation factors. So if you're inflating variance, this isn't a good thing. So, these mixture models by design have a lot of dependencies in them, and this makes us have to kind of do some different analytical techniques for them. So if you're creating a design, there's some very classic designs that are available to you. So if you look at the design on the left here, you'll note that if you have three components, X1, X2, X3, that you're trying to blend together, a de-optimal design is more often than not going to put things on the edges. Okay, so not necessarily at 100% of one and 0 of the others, but also it's not going to do much on the interior. So we find that more often than not, you'll want to do some space filling components in a mixture model. Because often what we're trying to do is find the optimal blend, right? So that's what the whole game is we need to characterize what happens as I start adding more and more. And it turns out that these points on the interior in the space filling world are much more useful to us. So optimal designs usually are going to put things on the edges, but what we need to do is kind of maybe work on the middle as well. So that's why we often have what we call hybrid designs. You create a design, an optimal design, and it gets all the stuff on the edges well, and then you augment it with space filling. So hybrid designs. So to do the analysis, we will do the regression analysis, but there's some extra steps that are involved here. Is we can't usually fit the intercept with all of the main mixture effects. And we don't necessarily do quadratic terms as much as the Cheffe cubics. So you can see a Cheffe cubic right here. It's rather than x1 squared, it's x1, x2 times x1, x2 interaction times x1 minus x2. So those are your Cheffe polynomials that come into play here. So when you start putting in some non-mixture factors, or process factors we'll call them, Then we start getting into some issues with some singularities. So if you do have some interactions going on, you can't actually estimate the main effects of those process factors. So some things start coming into play. And one of the takeaways from last year's talk was, this thing called self-validating ensemble models ends up giving us a much better analytical capability. So SVEM is self-validated ensemble models. Won't necessarily talk about that at this point. Maybe we'll hit it in a little bit. So what we did is, what is it? What's some guidance here? What works? Should it be D-optimal designs, A-optimal? What works best? So we did a bunch of simulations to figure out what the answer to that was, and kind of without getting too deep in here and trying to move along, this was kind of a key takeaway, was when we looked at the percent of max, which was higher is better, we kind of looked at a whole bunch of different options here, and the SVEM are these guys up here, the two different, so whether we're using the lasso, which we'll talk about in the generalized world, or just regular forward selection with SVEM, those performed quite a bit better. This is the sample size down here of your mixture model, compared to maybe your one-step, just a regular forward selection model. And then even the full model is green over here, and you can see that it does not perform well at all in many cases. So we kind of leave with, hey, SVEM is a good thing. So SVEM forward selection in particular we kind of like. And what's different about what we found out was that we need to uncheck the no intercept there. We can't actually run intercept models here. And we don't want to force all of the main effects. Those are the defaults. Kind of a thing. So let's see, some rules of thumb. We found that A-optimal designs in the mixture world don't really work too well. D-optimal is good. And we do like space filling designs in general when we're trying to find these optimal ones. So what did we ended up doing? We were able to well characterize a lot of the responses, because they weren't just looking for one response, they were looking for many different responses. So in this contour plot right here, it's what's my percentage of A1 versus B1, and we really were able to find some sweet pockets of operational or operability for them. And they really kind of enjoyed these profilers to see, where the steep curves were and what not. But let's talk a little bit about these models. I'm going to go back to JMP, and hopefully, so where am I? Right here, mixture models. So whiskey factors. Now you're talking. There's Coke, right? If you got Coke, you got to have Jack Daniels, right? So there's probably some Jack Daniels out there. I got some of mine, so Tom's got the bottle there if you need it. So, actually, no, I teach a class at Colorado School of Mines and teach mixtures, and somehow that seems to resonate with them. But imagine that a school that's right next to Coors Brewery somehow connects with whiskey too. So, but in this particular case, I've got three mixture variables. So, how much corn, rye, and malt do you put in your blend, and then how long do you age it, and then what kind of barrel do you use? Do you use American oak or French oak, right? So this all could perhaps influence your design. Now, what you'll note here is this tells me that I can go from 0 to 1. So what I'm going to do is I'm going to load these factors into custom design. So DOE, custom design, and I'll go ahead and load these factors, and we'll note that what I've specified these guys as is mixture, okay? So if you added a new variable, you would just, like for example, if I wanted to add a new factor, right there you get to choose, well, you would add a mixture, so if you want to put that in there. So that's how this becomes a role as a mixture. Now, you may not necessarily want to put 0 to 100, right? In fact, if you're Jack Daniel, you probably know a little bit more than that, and you might want to say, you know, I like my blends, but I want to have corn somewhere between 60 and 80%, and then 0 to 20 on these other two, or maybe even between 10 and 20 between rye and malt. But here it's kind of being unrestricted, kind of a thing. So now we can go ahead and say, you know, maybe I'm interested in some two-factor interactions here, and that's where I get the main effects were removed for non-mixture factors, where there's the interaction. So that was that. So here's maybe an 18-run design that I can go ahead and make. And not surprisingly, we have choices here. What do we want to do? Well, we've had good luck with D-optimal designs, not as much with the A-optimal, and I is nearly as good as D. So we'll keep it D-optimal design. So now I can make my design, and away I will go and figure out what my responses are. One thing that we'll note here on the power analysis, we aren't real excited about power when we start looking at the mixture variables, right? Because again, we have all this correlation going on, and correlation increases variance, and power is all about signal-noise ratio, so it all flows through that you don't necessarily have great power on the mixture models, mixture variables. So keep that in mind, that you could keep adding runs and still maybe never get to that 80%. So that's something that we ran into, because power is a great metric, but it's not the only one, and sometimes you have to kind of to balance some things out. But you can see the time by barrel here has almost 80% power for these. Why? Because time and barrel are not mixture factors. So now I can go ahead and make the table here, and then away I go. But what is of note in this D-optimal design is you'll see that it really didn't like anything in the middle at all, right? In fact, there is no single run in here that has all three of the components in it. So kind of the word to the wise is, would you want to do this? Maybe not, right? That if you really wanted some blends, you might use this as your core and then do some augment with your space filling design. So, but honestly, you would use Mr. Daniels' process knowledge and have him kind of narrow down some of these percentages for you. So let's do some analysis. So that's my design. And the next file down there is the populated version here, which will be blended whiskey. Blended whiskey. So now I've got my three responses here, which is going to be the viscosity of it, the color, and the aroma. So now we can go ahead and do our modeling. So we'll do analyze, fit model. And you can see that it's already pre-populated for us. And JMP knows that you created this design, and because you created it as a mixture design, it has already flagged that these are mixture variables. This is going to be very important for us, and we've kind of got all of these two-factor interactions in here. So now I'll go ahead and run. And we can see that there's a lot of these two-factor interactions that aren't statistically significant. We'll do a couple more, maybe up to there. Everything else appears to be, and this, by the way, is for all three responses. Okay, so we're kind of taking for each one of these. So maybe, you know, time is really important for the viscosity, but not so much for the color. I think we'll find out that's not actually true, that time is important for everybody. So we've got our parameter estimates here. So we can interpret the parameter estimates in terms of which one might be more important. Kind of, right? So that we see that malt is 2 versus 1.3 for rye. So that's maybe one way to think about it, and that all of these are statistically significant. But we also know that it might be better to visualize this. So if we visualize this in the profiler, we can see viscosities on top, then color, and then the aroma here. And we can see very wide swaths, right? We've got wide swaths because we've got lots of variance, because it's the correlation that's going on there. One thing we can do is, well, what's the most important factor? Well, it kind of appears like time is pretty important, right, in terms of the steepness of that slope. But we could have JMP figure that out for us, because if you look at the parameter estimates, maybe if you have nice scaling that Tom was talking about earlier, it's good that you can see that one might be twice as important as the other, but when you have an interaction going on, then all that goes away, and you're not really sure which factors are the most important. But you do have this option here where you can assess the factor importance, variable importance, and then I can colorize the profiler. And you can see across the different responses which is the most important. So we can see that overall it's really what barrel, using American oak or French oak kind of thing, is the most important kind of a thing. So we'll say aroma is good, higher aroma is good, so that means go America, right? That our American barrel beat out the French barrel. So we have to be careful of that because the Olympics are coming up, right? And they're in France, and I don't know if you guys looked at the NBA draft prospects, but like the top 10, like 4 or 5 are from France. And I'm from San Antonio, and there's like a 7'5" guy in San Antonio from France, so we could be in trouble. But we can beat them when it comes to aroma of our whiskey. So we can do the analysis in the standard way. But as I said, it's really the generalized linear model that ends up helping us out, and I'll show you an example of that as well here. So the next example is going to be this guy right here, the hypersonic fuel formulation. What I've done here is, so actually what happened is when I copied these over, all of these formulas didn't evaluate. So you need to hit the plus sign there for Y, and then the red triangle, and then the evaluation was suppressed. So now I actually have the responses in there and also the stoichiometry. So Tom brought back nightmares of your algebra class with y equals mx plus b, and I'm bringing back nightmares of your high school chemistry class with the word stoichiometry. Remember that? So this is a thing that I have up here. These are table variables. These are the molecular weights of these, of boron, carbon, and telluride. So all 3 of these, we have to be, when we mix them together, we have to be aware of how the weights come in. And that's what the stoichiometry is doing. So if I were to look at the stoichiometry, I would see that it's really the boron divided by its molecular weight plus the carbon divided by its molecular weight all over the telluride. So that stoichiometry is a constraint. So not only do I have the constraint that everything must sum to 1, I've also got another constraint in here based on the stoichiometry. Now, what I can look at is if I hit this guy right here, the ternary plot, I can see what my, that was not as good as this, maybe. So what the ternary plot is, it kind of shows you the 3 different mixtures, and then it says this white area is really the only ones that fit in terms of your stoichiometry constraints. Okay, so this is what the design came out to be. I told JMP that we need to honor this constraint. That's all based on the ratio of those molecular weights. So this is what JMP gave me for the design, and it is colored by the response, so you can see that lower values are down here, and then maybe in this neck of the woods is where the higher values are. This is one of those things that I have a mental block on, is how do I read a ternary plot? It's kind of not intuitive necessarily, but you can see that this particular point here, when we look at the carbon over here, it's 56% carbon, right? So if I just go directly across, that's the 56%. And then the boron is 18%. So if I take this value right here and I slide down parallel to this, that's 18% here. And then telluride is 25%, which is going to be going with this guy right here. So, meaning along this parallel to this guy. So it's kind of helpful to take a look at what your design space is, particularly your constrained design space. So ternary plots are big in, and you can look at, all four. I've got 4 components in here, so I can kind of see this little sliver here has to do with the polyethylene glycol, the PEG component in there. Sometimes we find that even though we have only a small percentage of a component, that ends up being a big driver. So even though I only have 1 to 5% of this, that its performance or its percent in there can be a big performance driver. So this is showing you a constrained design, and I just want to run a quick generalized here for you. So if I do analyze fit model, I can fit the standard least squares model, but what I want to do is I'm going to go ahead and for sake of argument, I'm just going to do a factorial to degree. I'm not going to do the quadratics or the Cheffets here, but I'm going to change my personality. In the afternoon, I changed my personality. So I'm going to change my personality to the generalized linear model. Oops. The generalized regression, I'm sorry. So I want generalized regression. And what generalized regression does is it allows me to do all sorts of options. And I'm going to talk a little bit more about this at the end of the day. But we can see right here that if you have a non-normal distribution, you can put it in right there. If you had censored data, you can put it in right there. Right now, what I'm going to do, instead of the 2-stage forward selection, I'm going to do SVEM forward selection. So that's a self-validated ensemble model forward selection. And then I go, and then I've created the model, and I'll go ahead and create the profiler. And here's what's nice, is essentially what that molecular weight stoichiometry said is that the sum of boron and carbon has to be less than the total amount of telluride. So as I start increasing my boron here to 52%, you can see how the constraints come in, how it doesn't allow me to do that. And it also keeps track down here of what these have to sum to 100%. So it keeps your constraints in there as well as sums to the 100%. And you can even put in more here, so you can alter the linear constraint. So here's where that constraint is, where essentially I've got my boron and carbon that's related to the telluride, all based on that stoichiometry problem. But as I said, we had 27 of these guys. So we had, our power for 84 runs was 0.05% for everything. So that's the mixture model world. Questions? Again, Tom has done a lot of stuff with mixtures too, and we're going to be here. So catch us if you have specific and want to go deep, take a deeper dive.
Maybe when I get back up, I'll put up some books. There is a book by Ron Sneed and Roger Pearl specifically on doing formulation. And Ron is a former statistician with the DuPont company who wrote a lot about mixture designs back in the 70s and 80s. So these are people who have been doing this for a long time, and they've kind of focused on JMP as the tool to help them do it. So there are textbooks on this as well.
It's for sure the most challenging in terms of the analytics. because you really don't know what's being masked, right? Because you got so much dependency going on. You're like, is it really factor A, or is it really factor B, or is it because as I increase A, I have to decrease B? So, and in fact, Ron Sneed is certainly one of the great fathers of the science, and there's another guy named John Cornell who has a text that probably will be on Tom's slide. But John Cornell ultimately said, you know, all of this stuff going on, maybe the best we could hope to do is not do any variable or model reduction like you saw me do. Just leave the full model in there and don't try to interpret coefficients. Just use it more for a predictor. All right, so don't try to say that, hey, that this ingredient is twice as important as that, and maybe we can't play those games. So that's where he left it. And then in the last 25 years or so, we're like, well, maybe we can at least find some insights. And that's where we found the self-validated ensemble model takes us into developing a little bit more consistent results that way to say, well, who really is the active player here? Mixture models. And there is another great article out there. I think it's How to Make the Ultimate Margarita. I don't know if it's Christine Anderson Cook might have written that or somebody. But next up, measurement system analysis, MSA. So here's where there's only 100 slides for me to go through. Only 100 in 10 minutes. So hold on, here we go. I think what I'll do, though, is I'll demo it first, and then I'll pick up some salient points in those 100 points, or 100 slides, say, hey, remember what we saw was this? So let's go ahead and do that. So two things with MSA. One, measurement system analysis. Again, it's like how good is your instrumentation? So if you have a lot of measurement error, you are going to have trouble figuring out what truly is going on in your experiment, right? So we want our instruments or instrumentation or TISP or whatever it is that we have that tells us what the value of the response was for that particular run. We want that to be very repeatable, right? So we want, if we do the exact same thing and there should be no other noise, it should give you the same result. So we want repeatability, okay? And we would like to quantify how well is our system, right? So a lot of people in the DT world in particular are very much on top of their gauge repeatability, reproducibility. Repeatability is how well, so if I'm measuring something, how well, if I measure the same thing, how consistent am I if I measure the same thing? Okay, reproducibility is if John and I are measuring the same thing, how close are we, right? So it might be always John seems to measure about, 20% higher than everyone else, or there's some bias that's out there. So by way of introduction, I think easiest to look at an example of this. So under 2.3 is this thing called instrumentation measurement accuracy. So I've got 3 sensors. Falcon 1, go Air Force Falcons. Hawkeye 2, Iowa Hawkeyes almost did it, right? And Husky 5, UConn. They won 5 titles until the 6th last week. So, see, I guess I didn't have much confidence in them because when I created this, it was before, so I thought they'd only have 5 titles, but they got their 6th. So, anybody from North Carolina? University, UNC? Anybody from Duke? So UConn has now eclipsed Duke and is right in line with UNC. So, but enough of basketball. So here's what we have: is we have 3 sensors, and we have 10 components that each one is measuring. Okay, and then we have the measurement here. So so component 1, so Falcon 1 measures component 1 3 times. Okay. So we had a question earlier, and it was, how many replicates do you do? What's the rule for that? And then, as all great statisticians say, it depends, right? So in this particular case, in the MSA world, we do like 3 replicates kind of as a minimum for this world. So now the question is, how consistent, because you are measuring the same thing multiple times, so we have that data. And we've also got what's the difference between Falcon 1 and Hawkeye 2 and Husky 5. So they're measuring the same thing, but are they telling us the same thing? So is there some systematic bias in there or not? So let's take a look. So we'll come under Analyze, and this is under Quality and Process. So, and we'll do Measurement System Analysis. So this is the analysis piece. So I want to show you the analysis piece first, and then we'll go back and catch on, well, how do you do the design? The design is fairly straightforward, so the DOE piece of this is not that exciting per se. So my response is going to be my measurement, and the part is going to be the component. Oops. The component is going to be the part, and the grouping is going to be the sensor. Okay, and we'll do this the old school way, gauge R&R first. So actually, yeah, we'll do gauge R&R. So that's all I have to do is cast those in there, and then here's some options over here when we're kind of looking at some capabilities and things like that. So let's see, use spec limits. Okay, nothing is going to surprise me when I hit OK here. So here is the questions. Let's see if I can get this bigger. Okay. So we have different components, okay, of what's going on here. We have part-to-part variability. So not every part has the same measurement, and it shouldn't, okay? But we've also got within the operator their own variability, and then we've got the between operator variability. So what you don't see here for Falcon 1, for example, on the third component, there's actually 3 rows that are right on top of that. So Falcon 1 measured 31 all 3 times. Way to go, Falcon 1. Okay. Contrary to that might be Husky over here. And Husky did measure 31 once, and then the second one was probably 32, or actually 39 looks like, 35, 33. So we can see what we would like is if everybody had a dot like this, and the dots were somewhat random, then we would have all part-to-part variability. But we don't, okay? What you could see here is it appears that Husky has a lot more variability than Falcon 1, correct? Okay, so this is kind of hopefully motivating it. And then this is what the standard deviation is across all the parts. And we can see that it's much higher here for Husky than Falcon 1, which pretty much had it nailed pretty well. So now, if I select under here, there may be under Gauge Studies, we'll do Gauge R&R. Gauge Studies, Gauge R&R. And we'll assume that this is a crossed model. What does that mean? Great question. So NDE, anybody heard of NDE? Non-destructive evaluation, NDE. So if you measure something and you don't destroy it, then that means Tom can measure, right? So if you can do that, then that's crossed. That means that everybody is measuring the same thing. But if I have something from lot 1 and I measure it and then it's destroyed, well, then we need Tom to measure something else from lot 1, and that will be crossed. If he's not measuring the exact same thing but something as close as possible, that would be nested, I'm sorry. So crossed is if we are able to measure the same thing. And that's exactly what is going on here. So we'll just leave that alone. And here's my gauge R and R. So what we have is the variance components down here, okay? So ultimately, what I've got is 79% of the total variability in all this data is attributed to the part-to-part variability. This is a good thing, okay? And I've got 10% is due to the repeatability of the individual operator. And then we also have the reproducibility is 10.7%. So the 10.7% comes from the variance component. It's right here. It's the sensor and the two-factor interaction, sensor by component. So if you sum up both of those, then you take the ratio of all these guys. So the repeatability is just between the average of each of the operators, and then the reproducibility is for the sensors and the interaction with the component. So you've got your part-to-part. So what I think I wanted to show was in that there should be a good plot. What I wanted to show is that we do have a bias in here, okay, that maybe someone is always measuring a bit low, someone's always measuring a bit high. So what I'll do, I think there's a good view of that if I come back under Analyze and Quality and Process, and this time we'll do Measurement System Analysis, Recall, except I'm going to do the EMP. So this is from Don Wheeler in 2006 kind of wrote a book, and it's sort of the current thinking of how we do gauge R&R. And this is crossed right here, and maybe even we want crossed with the two-factor interaction. So I'll go ahead and do OK. And so here's the ranges that we were looking at, and they put little control charts on here too to see if you've gone out of control. But the plot, I think, of interest is going to be this guy. Let's see. Yeah, so there's our gauge results there as well. Ah, there it is, parallelism plots. So this is the other big thing that you're looking for, is how well is your instrument measuring what it's supposed to, right? So there's a part of the MSA world where you can actually, if you do have truth data, that you can well quantify that. But in this particular case, we can see that Hawkeye is always low, right? So there's a bias that the Hawkeye is always measuring low, kind of a thing. And then maybe Falcon 1, we can treat that as truth, for lack of a better, because why? Falcon 1 was pretty consistent and sort of seems to be in the middle there. Maybe Husky has a tendency to measure high every now and then, but for sure, Hawkeye has that bias in there. And we can do estimates for what that systematic bias is as well in our instrument system. So what you want at the end of the day is to be able to say something like, of my total variability, right, that most of it is attributed to the part-to-part, okay? And again, you're not all making parts, I get that, but you are doing things that are being measured, right? And then you have is it run-to-run variability, or it's the environment-to-environment kind of a thing, right? So, but what you don't want is it to come up from your gauge or how you're measuring things. So if you can partition your variability that way, that ends up being enormously helpful. So then you kind of take a step back and say, well, wait a minute, how would I do that in my test? I'm already, up against the wall trying to ask for 15 runs, and now you're telling me I need 3 for each one. And so in many cases, this is a function of, folks in the lab, so to speak, to make sure that their instruments are tuned properly. Gauge R&R. Let's look at how you might set up a design for that. So if I come under DOE, And then there is this thing that is called a special purpose. DOE special purpose, and it's going to be measurement system analysis design. So we've got a response here, and I'll just call it measurement. And we're going to add a factor. And we call that sensor, right? And the sensor was our operator in some sense, right? So that's going to be our operator. Then we'll add another factor, and that's going to be the component. Okay. And by the way, the number of levels for sensor, there were 3, right? There was Falcon, Hawkeye, and Husky, and we had 10 components. And then we had 3 replicates done, right? So JMP calls a replicate is after you've done 1, then you do 1 replicate. So this is really like doing 3 runs. So 2 replicates equals 3 runs, kind of a thing. So anybody use Statis, the design expert? Yeah, so they do it, that they would put in 3 here for replicates, kind of a thing. So in this particular case, there's a couple different ways that you could have this, whether you want it completely randomized, batch repeat, or fast repeat. I'll show you real quick on a slide when we get to that. It's how do you want to do this? Do you want to measure all the parts first, or have an operator measure all the parts first, or have every operator measure that same part first? What's your scheme? Or would you like it completely randomized? Guess what is best? Did we say we like randomization in here? We love randomization. So we'll keep it with that. So this is your nested structure or not. We don't have anything, so if I don't do anything here, it's going to give me the crossed. So everybody's going to be able to do the same measurement on the same component. If I had some structure in there, I could put it in right here if it was fully nested. In other words, doing destructive evaluation. So I'm going to go ahead and make this design. Okay. Kind of jumped the gun here. So this role here for component is really the part. So at a minimum, you have to specify your part and your operator. So now we make this design, and here's our table. And I go ahead and make the table, and there is my 90-run design that we just analyzed, okay? And you'll note it is completely randomized, right? So sensor L3, which would be Husky, would then look at component number 4. And then the next run, so you may not see that as a good way to run things. So that's what these other options are. So not much excitement there in terms of having fancy algorithms. It's relatively straightforward, and it's based on how you want it ordered. You can create an operator worksheet here. So if I open those up, so this is for my Husky. Here's your 30 runs that you're going to do, right? So you can see that in here, sensor is always at level 3. So this is, I'm going to hand this to Husky, say, here, go ahead and measure these 30 components. So that could be helpful for your team. MSA, questions on MSA? Something could be helpful for you?
Is the analysis a random effects model? Because you're saying variance components?
Yes, it is, definitely. Yeah. So it is
It's just
random effects.
every factor is a random effect.
Yes. Yeah. Now, thinking about it, if there were only 3 sensors, right, we could go in and change that to the fixed effect. But if these are like typically operators are randomly chosen kind of thing. So
If you had 3 operators for each, for Falcon 1, you had 3 operators.
Uh-huh.
Would they both be listed in your, in the setup as operators? Like this Falcon 1's an operator, and then the executor or
Right.
administrator would be an
John, Tom, and Jim would then be nested underneath Falcon 1. Yeah, and that's where we would do that nesting structure. Yep. MSA. So we good for our next one? Next up is, actually I did say I was going to show you something real quick, so let me not go back on my word. So MSA. So here's what you don't want, right, is anything other than the Northwest. Northwest is good. Other than that, you're kind of, you're doing pretty well in terms of not much variability, but you're biased, right? And then here you got a little bit too much variability, and here you got both things going wrong. So we want to kind of be in the middle of that. So let me see if I can find. Fast repeat. Here you go. So this is the fast repeat. We did completely randomized, but you could do a fast repeat. And what you have in the fast repeat is you pull up part L1, okay, and then you've got operator 3 does her 2 measurements, 1 and 2, and then passes it to operator 2 who does her 2 measurements, and then operator 1 does his 2. Okay, and then you get the next part, and then you cycle through it quickly. So it's kind of like do the part first, and then move on. Different from that is the batch repeat here. So what I'm going to do is I'm going to have everybody do all of their first measurement. So we're going to go through all 10 of the parts, or however many parts we have. They're going to do that first measurement, and then almost like that's block 1, and then block 2 is going to be your second replicate. And then you'll note even here that you're going to take all, part 2, all of us are going to do that. And then we're going to go to the next part. All of us are going to do that. So if that scheme works for you, then that's, a potential option rather than doing the completely randomized, which is this guy. So anyway, 100 slides in there for you to peruse. And ultimately, we didn't get too much into it, as much as me saying it's really good to have your part-to-part variability high percentage, and then your gauge R&R to be low. Well, there's different ways that we can kind of play with that in terms of your intra-class correlation kind of a thing, as well as your precision over tolerance. So there's some of these guys here, your figures of merit. So in other words, if we look at the intra-class correlation, which is going to be your variance of your part over your part plus gauge, so your hope is that that's very close to 1, that all your variability is due to the part. And then if you are, you're first class. If you're less than 0.2, you're fourth class. So. Did anybody go to like West Point? Where'd you go?
I taught there.
Oh, you taught there. And there's fourth class, right? Fourth class is a freshman. The plebe, yeah. So you don't want to be fourth class. You want to be first class. If you're fourth class, then you probably need to work on that measurement system. And there are ways that you can, let me see if I can show real quick. I guess it's not in here, but it is in here, but I don't want to find it. The bottom line is you can tell whether or not your system is correct in terms of its precision. What I mean by that is, are you measuring too many decimal places, or do you not have enough decimal places accuracy? Right? So you're able to tell that through these gauge R&R studies. MSA. Highly recommended. And a lot of folks should be doing it that aren't. It's kind of surprising. Okay, next up should be accelerated life tests. When's our break, John?
2:30.
2:30? Great. Design and analysis of accelerated life tests. All right. So what happens in the accelerated life test world is we don't have enough time to wait. Okay, so for example, if you were trying to determine how long it is going to be until your hard drive fails, you may not want to wait that 4-year test period or whatever. So maybe we know that a failure generating mechanism is temperature. So instead of having it sit here at 68 degrees, it's about a little chilly in here, isn't it? 68, 69, and rightly so. For those that had too much Jack Daniels in the Coke at lunch. So why don't we test it at 100 degrees? Because that's going to precipitate that failure a little bit quicker. We don't want to test it at 2,000 degrees because that really wouldn't give us much information, right? So that's kind of the trade space is, okay, I want to accelerate the operational environment. So for my friends over here from the Marine Corps, you don't like this idea probably because I'm going to break outside of the operational envelope. So this is not going to be too realistic. So the OT community, you might not be wanting to do a lot of this accelerated life test, okay? But it's worth understanding that it's a capability that exists that could be useful. And it's really more of a reliability thing. And I don't, when I was at Aflatech, we had a lot of, and I forget what term we used it back in the day. And anyways, it was not observable. So in other words, we had a mean time between failure of 5,000 hours. Well, our test was 100 hours, so it didn't fail. So did we pass or did we fail? It's like, well, we didn't run till failure, so I guess we passed. So what we could have done is done some accelerating life test, and or at least use the DT data to kind of give us an indication as to this is how we think the reliability will be for that suitability evaluation. So let's see, what I want is accelerated testing. You're accelerating life if you're living here. That's a Buddhist temple in Bhutan. Bhutan is a country by Nepal and Bangladesh, and it does not have a measure of GNP. It's GNH, gross national happiness. So, I mean, this is true. That their money is, you know, it's important, but it's really about the happiness. So what makes us the most happy? So, this is a temple up there. It's called the Eagle's Nest.
The University of Texas in El Paso, their architect is based on that.
Oh, really? I did not know that.
On the top.
Yes. It's a wonderful place. I didn't want to leave last year. So accelerated testing. So the idea here is that we are going to try to bring things back into real life based on what we learn from an accelerated operational environment. So what are some stressing factors? You know, temperature ends up probably being the number one enemy to reliability, as many of you probably are aware, right? Even in your car. When I was at Arizona State, it was always the first 100-degree day that lots of people's batteries didn't work. So they were okay, and then, in fact, it's coming up now, like maybe middle to end of May, it's 100 degrees, and bang, battery died. Temperature is the enemy. But there's other stress factors in here that we need to account for as well. And there's different types of stress, whether it's a constant stress that we're looking at, that we're going to apply, or maybe it's a step stress. Like, okay, we're going to start, if we're talking about that example with my hard drive, we'll start at 100, and we'll do that for a month. And then we'll crank it up to 120, and we'll do it for a month. And we'll crank it up to 140, and so forth. So that's kind of the idea of step stress. or you can do kind of a ramp as well. So ultimately, there's really two primary relationships that we do in this accelerated life test. And the first one is the Arrhenius model. The Arrhenius model we'll talk about here in a second, but it really is that transformation that we need to take. We know the degradation pattern follows the Arrhenius model. Similarly, like voltage is going to follow a log model. So we know this from physics. So we're kind of tying into what we know to what we don't know. And you're going to see that that kind of is a big theme for a lot of these models. But you can see we could also do any other of these transformations that we want. But by and large, most of these accelerated life tests are done with Arrhenius for temperature and then log otherwise, because log is kind of like a power model. So here's the Arrhenius relationship right here. So this is kind of like your time to failure, if you will. Your time to failure is A, which is going to be specific to a particular part, and we're going to estimate that from our data. And then negative E is the activation energy, and then K is Boltzmann's constant, and then T is whatever temperature you're at in Kelvin. So the whole idea is we need to take advantage of this known relationship when we do our projection. So here's my Arrhenius acceleration factor. So you can see it's really just the ratio of your temperature use case versus your accelerated temperature. And that ultimately comes out to this guy, this relationship right here. So let's first maybe look at how this works in terms of if I've got accelerated life test data, how does it all fall out? And then we'll go back and say, well, how do I create a design that's going to help me do that? So let's go ahead and open up this guy here, Arrhenius data. So let's say our use case is 100 degrees, but we tested here at 150, and then we got a series at 175 and a series at 200. Okay, and then it tells me when did it fail. And in reliability, we have this thing called censoring. Sometimes things don't fail. We have to stop the test, and if it didn't fail, then it's censored. So 1 means that it did not fail. So we put these units on test for 2,000 hours or 2,000 cycles, and this particular number 5 did not fail, nor did number 2, kind of a thing. So what we'll do is we can fit this model. So we'll come and do analyze, and this is where we're going to use reliability and survival, and we're going to do fit life by X. So I know is it Charles that was talking about he's got survival time as part of his world. Well, reliability and survival are the same thing, just kind of complements. So. Okay, so my time to event is going to be the temperature. Actually, no, it's not. It's going to be the failure time. Temperature is going to be the X, and sensor is going to be sensor. And then it immediately defaults to 1. So you could have some other censoring pattern, but 1 is what we're going to call it. And we need to figure out what is the relationship of interest here, and this is where I'm going to choose Arrhenius Celsius. Okay, and the nested model test, this is different from the nested versus cross that we were just talking about. Okay, so we're back. We'll go ahead and use the log normal distribution, and just for fun, we'll do likelihood. Did I ever say I like likelihood? We'll do likelihood. We'll do okay. And what we have is this plot right here, and what I'm going to do is I'm going to expand it so I can see 100. But I'm going to have to add a quantile. So under scatter plot, I'm going to go ahead and add a density curve at 100. So again, I'm going to use this component at 100 degrees Celsius. I did not test it at 100. Again, I know my operational testers are just cringing, but that's okay. This is all about projection, okay? But it's projecting smartly because I know the failure mechanism in Arrhenius Celsius is well documented, kind of a thing. So I'm going to go ahead and add the quantile lines, and I'll just use the 10, 50th, and 90th. So what that is showing is we can make, I guess none of that showed up. You guys can't see what I'm talking about. Let me see if I can change this color. Maybe not. No, not easy. But anyway, you don't see it, but there actually is a curve right here. And it looks like this. So that curve is what I'm trying to, that's what I care about, okay? And I'm using this test data to generate this curve right here, okay, that you can't see. And the good news is that I have lots of information down here that will help me do so. So I can see right here that these do kind of look like they fit fairly well. But you know what? Maybe I would like to try a Weibull distribution. And if I do Weibull here, maybe that's a better fit, maybe not. And if I come up here, my comparison criterion, you'll note that log normal is less than Weibull. This is good. The lower, the better. So log normal is what we're going to run with for this particular example. So I've got my log normal results right here. And this is my Arrhenius model. So remember, I'm trying to estimate that capital A. Okay, I'm also estimating the activation energy right here. Okay, and this 11,065 is constant, so no matter what, it's going to be there. And this is the overall, kind of like maybe the slope of the line, you can think of it as, but the overall variance or standard deviation kind of a thing. So this is my Arrhenius Celsius model. So I can use that and exploit that to kind of project into my world. And what do I mean by that? Is, let me get my, close down Weibull, come back up to log normal. And let's see, where am I looking for? I was looking for my densities. Okay, so I'm going to come back down here to my log normal results, and it's tabbed is what I was looking for. So here's my distribution. So what I want to do is I really am not too interested in 175 degrees. My use case is 100. So at 100 degrees, my probability of failure at 1,000 hours is nothing, 10 to the negative 30. Right? So remember, I only ran this test, what, 2,000 hours? So there's my 2,000 hours, and you can still see I got no chance of failure. So the only way I was able to create this distribution was to crank up the temperature, okay? And then now maybe at 100,000 hours, I've got a probability of failure. Now, so I've got almost a 1% chance of failing at 100,000 hours. Who has 100,000 hours to wait around for this to fail? And you only got a 1% chance that it will anyways, right? So the only way that we're able to develop these curves and come up with these profilers is through the accelerated life testing. Pretty neat, right? So what we'll do now is, let me look at that log normal. stats here for the log normal. Yeah, okay. So the question is how do I create these designs? Okay, so now that we kind of understand what happens when I get the data, I can get the data and then I can project back into the real world. And one thing you may want to do is figure out, well, what is my expectation at which maybe 10% of these will fail? That's called the B10 life. So you can kind of, on your quantile, I'll put in my probability here of 0.1. So I believe that 10% of these will fail at temperature 100 at 175,000 hours. So very, important result there. Now, clearly, if I'm up at 175 degrees, it's 117 hours. That I can deal with. 117 hours, we have that amount of time. But we don't have 175,000 hours. So that's why we have to do this. You can also do custom estimation in here. So, maybe you want the median failure time at temperature 124, kind of a thing. So then that gives you all those statistics as well. And what's pretty nice about this is you can say, well, okay, if I made it, if I've already survived to 2,000 hours, and my temperature is 125, what's my mean remaining life? So at 125, you've got 23,000 hours left. So you can kind of play these games. This is the end result, but the question is, how do I know how to set these up, right? So I can do a DOE on this. So let me look at one more thing here. Capacitor. Okay, so let's do the DOE of this. So I just come under DOE, and then again, it's a special purpose, and we'll do accelerated life test design. So in the accelerated life test, we'll just do the initial one for one accelerating factor, but we could do two if we wanted. And that factor name will be temperature. And we'll do 3 levels. And we'll do the Arrhenius Celsius, okay? The low use condition, we'll say that was 100. And the high use condition also will be 100, right? Maybe 80 to 100 or whatever, but we'll just put it 100 there. The test condition, we want to go from 150 to 200. So now I'll select continue, okay? And here you get to choose. Do you want a Weibull distribution or log normal? So many of you have heard of life is not always normal. So who deals with non-normal data? Who uses distributions other than the normal distribution? So what are we using? We're using log normal, gammas, whatever's available and fits. I'm with you. So life is not a bell-shaped curve. So we generally, in reliability, we believe, I think Bill Meeker has stated that maybe 90 to 95% of all data, of all reliability data, can be fit with a log normal or a Weibull. So, and in fact, depending upon the parameters, a Weibull and log normal could both be normal. So you can kind of shape it into what you need. So we're not necessarily limited by only having log normal and Weibull, because that's typically the way things are going to fail. So now we could have our priors. So the question is, what is a prior? So we have to have some previous information in here, perhaps, right? So we could specify the quantile. So we, say, well, at this time and this temperature, we would expect, 6% to fail at time 2,642 at a temperature of 45. So those aren't good default values for us, right? So what did I say? I said that the B10 life, so we'll say 10% are going to fail. And was it 125 that we did? I forget. So I did a custom estimation in here, I think. Well, for sake of argument, we'll put in 2,000 hours at temperature 125. Now, what I can do is I can actually, that data that I just showed you, I can no kidding put in those parameter values and the covariance matrix by hitting this specify the prior. So that's these guys right here, and then this is the correlation matrix. So what I'm saying is when I look at the statistics back here for the Weibull results, we'll say, these guys right here. So I have these guys, they would go right here. Oops, no, the uncertainty, not those. They're standard errors. So the standard errors would go right here. And then the correlation, those covariances, that's these guys right here. Right there. So this is your prior information. So if you have it and you have data that you run, you can integrate that into what this design is going to give you. Okay, rather than having a balanced design that if you've got 100 articles that you're going to do 33 at 150, 33 at 175, 33 at 200, might not make much sense. Why? Because at 200, you know they're going to fail pretty quickly, right? So now, maybe how many units total do I have? I'll do 100, kind of a thing, and the length of test, we'll do 5,000, we'll say. And we'll go ahead and make this design. And we'll make the test plan. So the test plan says that I should do 79 at 150 and 21 at 200, and not necessarily anything in between. To be honest, I think if I had put in the real data, those coefficients, in the interest of time, I didn't, but I did, it would have been, I think most of them would have been done at that middle 175. But in this particular case, the way I specified the failure distribution, that was there. So I did want to show that. So that's my, but that's not the table necessarily, that's the test plan. So here is the actual, okay, now go ahead and collect your data and tell me when it failed, each one of these hundreds. And we can see that the distribution is not consistent. Well, you can't, but if I highlight it here, you can see that there's that guy and that guy. So, accelerated life test, exposure to it. Understand that it exists, and there's a fairly advanced capability that's implemented in JMP. I would also say that people in the hall, down the hall, that are doing R, that is probably in there as well, because I know Bill Meekers does a lot of stuff in R for development type things, and I think he was the consultant on this. So there should be lots of opportunities to do accelerated life tests out there. But recognize, accelerated life test doesn't mean just doing an equal number at each of the accelerated environments, that you need to figure out a clever way to do that. That's where you bring in your old data. If you don't have old data, then that's when you can guess on what you think. Talk to your subject matter experts. What do you think, how many would fail at this level? There also is something called a step stress. So step stress is done under the cumulative damage, and you're able to kind of track it along the way. I'll just point it out that it's there, because it looks like I'm running well behind schedule, as always. So here's the step stress pattern. So actually, I'll open that up as well as the step stress data table. So the data table is actually showing the failures, so whether I was in pattern 1 and then when it failed or it's censored. So a quick view here is if I do analyze reliability and survival and come under cumulative damage, okay? Now I actually have to select a table. So the time to event table, that's going to be step stress DT. And my time to event is going to be time. Sensor is going to be sensor. And pattern is going to be pattern. And then I select another table right here to say, well, what is the pattern? What do my steps look like? Okay, and I'll show you what those steps look like here once I enter this in. There's my pattern. And stress duration is duration. Stress is voltage. And pattern ID is pattern ID. So off we go. Pattern ID do not have the same type. All right, so let's put that down. Step stress pattern ID, we'll change that to continuous. And that should fix the problem. Where did that interface go? Come on. Let's see, where'd you go? Capacitor. All right, we'll start over. Quickly, analyze, reliability and survival, cumulative damage, recall. And that should do it. Okay. Not sure how that ordinal got in there. Okay, so this is what I'm saying, is that you could have different patterns of your step stress. So this is how much your cumulative time that you're on test. And you can see that pattern 3 is, I'm really cranking up the voltage here. So we kind of start out at just 0.01 and then I crank it up really quick. Versus pattern 1, I'm just kind of slowly increasing it over time. And then I can do my analysis here to figure out where, ultimately what my probabilities of failure are and my use case back at 4 volts or whatever it happens to be. So that's the step stress version. Nonlinear. And that will take us to the break.
Wanted to add one more thing, that last year at DataWorks, there was a 90-minute Bayesian tutorial on reliability analysis that was conducted by the developer, Hong Lu, who's behind a lot of the reliability platform, and that recording is available. So if you are more interested in reliability analysis, particularly if you're trying to do it more from we do have some prior information, how can you leverage that to shorten your reliability testing? So make sure you're aware that that resource is there.
So the nonlinear world here, a lot of people are doing binomial type stuff, right? So you could have a binomial predictor that you can use to help develop your design experiment here. So let me just jump right to it because we're running quite a bit behind. And I do want to show a few different things here. So let's see. So here's the, so what we have is a 2 factors here. So this is my core quality. This is the NASA rocks again. So it's 2 input factors. Is going to be the average cycle side lobe and then time in hard rocks. Okay, and then that's ultimately going to result in some core quality. So what happened is I have previous data and I ran the logistic regression on it, right? So we know we get those parameters from the logistic regression, and that's what this is right here. This is the parameters from that logistic regression that fit. And you'll note right here, beta naught is -5, beta 1 is 0.25, beta 2 is 0.015. So this is the coefficient associated with the side lobe, and then the hard rocks is 0.01. So as you know, logistic regression, you're not modeling y, but you're doing this response rate, this transformation, 1 over 1 plus e to the, so this guy right here is what we usually think of as our beta naught plus beta 1x plus beta 2x. That's this piece in here. So I've got that in there, so I'm all ready to go. So I can do DOE, and then I can do special purpose, and this is where I'm going to jump into the nonlinear design. And the nonlinear design is looking for a response, and we're going to call it our new response. But it's looking for the prediction formula. So you have to create that prediction formula. I happen to make it because I did a logistic regression. But there's a nonlinear platform in here. You can make it any way that the Arrhenius-Celsius, that function, you can make it any formula you want in here. Okay, so I'm going to go ahead and put in logistic reg model in here. And honestly, we should create a new weight here, but we won't. But what happens now is I now have these parameters, and do you see how it goes from -2.5 to -7.5, 0.125 to 3.75? That's a pretty wide swath. So this is what we'll call a diffuse prior. So this is kind of like Bayesian that we're doing here. So this is a diffuse prior. If you're really sure what the true estimate here, so the beta that I saw from my logistic regression was the center point in here. So you could bring it in, and that would make it have a diffuse. This is diffuse, but you could have a much tighter based on what you put in for these parameters. So now I just go ahead and make this design, and then I'll go ahead and make the table, and you'll note that this is what you will run for your designed experiment, taking into account the overall nonlinear and the linear predictor coming from your logistic regression suggests that you should be doing these runs, which you can kind of see are fairly full factorial plus this guy here that's slightly off. So it's as simple as that.
So then with set of prior, does JMP have functionality for testing if the prior you set is good or bad? Like, is there any sort of sensitivity analysis? And then you could see the outcome of setting a prior to different values.
So you've set this up, now you collect your data, and is there a way to go back and say, wow, we kind of really missed with this?
Yeah.
I don't know that there's an inherent capability that is there to do that assessment apart from your own, because you can see right here, this last column is exactly what your prior is predicting, okay? And then now you go out and then you can go ahead and figure out, of course, your response is going to be ones and zeros. Was it good or was it bad kind of a thing? So you can see, well, anytime I'm greater than 0.5, I should be a 1, right? Assuming that was you use the default, and we can talk receiver operating characteristics and things like that. But you can kind of play that game too to see, well, ooh, looks like I really, missed the boat here. And then that would be more of the, okay, you're not going to undo the runs you did since you've already done them, but it would well inform your next step in terms of figuring out what your augment scheme is going to be.
We've got Brad Jones queued up. You've heard his voice, and you may have seen his picture on the screen. At 3:15, he's going to be available to address some of the questions we've been putting on the whiteboard. And again, this is the journal that Jim put together, and there's lots of topics here we just didn't have time for. So if you see a topic, feel free to reach out to me or Jim about it. We're here for the next 2 days. Again, my job is actually to support the defense and aerospace industry JMP users, so I frequently go on site or do remote sessions with people. So we're happy to continue to support people that didn't get to see everything they wanted here. So I've just jumped right into a middle of a slide deck on modern screening design to kind of focus on this slide that when I had it up earlier today, I said it was one of the most important slides at the beginning of the day, to realize that the algorithmic design, the custom design capability, the optimal design capability, however you want to call it, in JMP is really aimed at, solving problems where you make your design fit that problem, as opposed to the idea of taking sort of a textbook design and trying to make your problem now fit the available designs. Well, where we're headed next is talking about different screening design methods. And again, we have a very limited amount of time here, but I'm going to focus a fair amount on the definitive screening designs and then talk about some of the other screening designs available in JMP. And in particular, the question came up here, actually a woman coming right to her seat in the front row, I think may have even said it. All of my factors are categorical. How do I make designs for those situations? So we'll talk about these orthogonal array designs that are in JMP. And we even have design methods for when you have lots and lots of factors. There's a group orthogonal supersaturated designs. Somehow the time has gotten away from us here. We've got, minutes away, and this alone could take a few hours. So we'll be here till midnight. So I'm just going to jump in quickly with this comparison for some six-factor designs. We've mentioned Plackett-Berman earlier. We've also mentioned fractional factorial, but definitive screening and design, it was developed by Brad Jones and Chris Knoxheim back in 2011. They published their paper on it. And I just want to compare the color maps here, where both of these designs have 13 trials. The Plackett-Berman one on the left has all, high and low levels and one global center point. The one on the right, we're going to see in a minute, has many more mid-levels. But the main thing to see in this color map is that this area here, where the main effects are orthogonal to each other, that's true over here on the definitive screening side, but it's this area where the interactions are partially correlated with the main effects would make most people lean toward the design on the right. Certainly makes me lean in that direction. And the other thing to keep in mind is that the definitive screening design gives us a test for curvature in every factor, not just for a global check with one center point. So a lot of people might have said, I tend to go more toward fractional factorial classic designs, where I do have that same situation. My main effects are not confounded, and they're not confounded with any of the two-factor interactions, even though there is some complete confounding of those interactions with each other. You can see here that the definitive screening design would have that same relationship in the main effects and interactions area, although there are partial correlations, but no complete confounding among all the two-factor interactions. Well, the design on the right is 4 fewer tests, and I get the test for curvature in each factor. And so, since these definitive screening designs came out in about 2011, if I am sort of not in the custom design mode, okay, so if you're in the screening mode here, you're limited to continuous factors or categorical factors at just 2 levels. If you don't meet that criteria, you're not going to be able to use the definitive screening design. But given that situation, I'm much more inclined to use these newer modern screening designs like the definitive screening. So do we give up nothing if we're using definitive screening designs? Well, relative to the same size classic 2-level screening designs, you're going to find things like the confidence interval increases, typically less than 10%. Standard error increases, typically less than 10%. Power is reduced for main effects, again, typically less than 10% if you're comparing to the main effects. And maybe one of the criticisms that people have always said about the definitive screening design is that the power for the squared terms is low, and that's true. There aren't that many mid-levels, but it's still way better than the power for a single point test for curvature you get when you add that onto a fractional factorial or a Plackett-Berman. And if you actually start calculating the power for some of these designs, you'll find that the power is the same or larger than even some designs that people have used for years, like central composite designs that support full quadratic models. And the other thing to keep in mind, anytime you start dropping terms from your model, the power increases for those other factors. So again, I don't have time to go into slides on this, but we can show you how the power increases for these definitive screening. So for me, the real weakness, if I had to say, well, what are the weaknesses here, is if you've done your screening design, okay, and if you've been lucky it's collapsed into supporting a response surface, and if you're not that lucky, I showed you earlier how I could augment a design up to support more terms in the full response surface model. What you really can't do, you can't do that if you change your ranges. So if you're very early in the development of a technology, you might not have your ranges nailed down. But by the time you're doing testing in most of DoD, this is no time to change the range of the elevator, on an airplane. I mean, that was locked in years ago. So you're not likely to be changing your ranges at that point. So the more you are in early product development, maybe the less likely you're going to be, you're going to have issues with augmenting a DSD. Okay. I also want to introduce pretty quickly here a new design that's in JMP 18, and they're called orthogonal mixed level designs. And if I make some comparison here to the, when I say the older, the 2011 DSD designs, along that path over the last 13 or 14 years, they added the ability to handle categorical factors at 2 levels to the DSD. But when you look at these new orthogonal mixed level designs, you're going to find they have better power overall, but especially for the quadratic terms. And so if I drop out and make a couple designs, you'll see why. They have more zeros in them. And anytime you add more zeros to the mid-level of the design, you're going to improve the power, especially on those quadratic terms. So here I'm just graphing, if I were to take a 4 continuous, 4 categorical factor problem and make an 18-run definitive screening design and compare it to an 18-run orthogonal mixed level design, you're going to see that the big increase is in the power for the squared terms. And if you look at that fraction of design space plot, where again, lower and flatter means we're predicting the variance better across our design space, you're going to see that that's improved as well. So let me just maybe drop out and make a couple designs so you see how we do this. And I was trying to clean up my background here a bit. Got a lot open there. Okay, getting there. All right, so if we were to go to making a definitive screening design, you can see it's got its own menu item here. And if I were to make I'm going to do 2 different types of designs here. So first I'll just do an 8-factor all continuous design. And you can see here that we default to having no blocks and the number of extra runs. The extra runs are there to 2 things. One, it will increase the power, but the other thing is with the sort of, there's sort of some extra information there that allows an automatic fit definitive screening method that's very robust, okay? So most often people would go with the default. And in this case, I'm going to set it back to 0. This is still a perfectly good definitive screening design that it'll generate. But the main thing you can see are these diagonal zeros. But you'll notice there's only 2 out of the, there's a row of zeros at the bottom. That's the global center point. And so you can see the, we've got some tests for curvature in every factor. And this is where, if you're lucky, typically for 6 or more factors, if there's only 3 factors that are important, it will collapse into supporting a response surface design in that particular case. So that's sort of the one-shot design idea. Okay, and if I go to the color map, I showed this earlier, you can see that this area here is all white. So there's no confounding at all among main effects and 2-factor interactions. Okay, let me just make I'll do that same type of design, but now I'm going to have 4 continuous and 4 categorical. But notice here when I click categorical, I don't get a list of how many levels that you've been seeing that in the past, because you're only allowed to have 2 levels here. So once again, if you have a 3 or 4 level problem, you're not going to be doing a definitive screening design or an orthogonal mixed level design. But if that's all set to go, we'll do the same thing here, make the same number of trials. And the difference here is you can see there's only diagonal zeros up here on the continuous factors. 0 makes no sense for the categorical. Okay, and so if I make, I'll just maybe bring that power analysis up where we can see it. Actually, I'll make the table for it. And now my table is by default randomized in JMP, so I no longer have everything on the diagonal. Let me go back and make those, so they're not, still didn't do it, did I? I was trying to get my, oh, the original design is in a randomized order. Okay. I'll just leave that here. Okay. I know I'm trying to get this all in 15 minutes on modern screening. Let's go back and now do, and this is well hidden, okay, under classical factor screening, screening design, okay? And again, I'm going to have 4 continuous factors and 4 categorical. This time I am going to pick at 2 levels. And when I go to the next setting here, I've got some choices. The default is choose from a list of fractional factorial designs. Those are the classic screening designs, okay? You could construct a main effect screening design, and that's what we're going to do as a quick example of how do you handle problems where everything is a categorical factor and they're at lots of different levels. But the new one in JMP 18 is this construct a mixed level screening design. And there are 3 choices here for the construction type. The one we're interested in this case, is the middle choice, where you can see the number of runs has to be a multiple of 8. And so we've got this 16-run design. And when I make this design, you can see that the number of diagonal sort of rows of zeros there, there are 4 sets of them, which means there's twice as many zeros in 16 rows here of design. And so if I were to add 2 rows of all zeros to the bottom with all at the high and all at the low on the categorical, I would reproduce what I had in this slide, which was here, I believe. Okay, so it would reproduce this case here. And so that is how you get that higher level of power for the quadratic terms. So when would you use a definitive screening design? If everything's continuous. Definitive screening is a better choice if all the factors are continuous, because you check for curvature in all factors. These orthogonal mixed level designs require multiples of 2, 4, or 8 factors to achieve balance, and they don't always add the center points for all the continuous factors. So just pointing out, it's a brand new design, so it's, I guess they probably published it last year, but all of these are sort of special cases where you can do a little bit better if you know this design is available. Okay, the last one I want to squeeze in here is this idea of comparing an optimal design, which I've told you before, that's like your 80% solution. Most of the time, it's going to give you a workable design. So in this case, we're going to have 6 factors, but you're going to see that there's 1 at 2 levels, 2 levels, 3 levels, 4 levels, 5 levels, and 7 levels. I've got that all stated there. So let me go out and run that situation. So we'll go to DOE, and this time I'm going to go to that classical factor screening design, and I think I had a continuous, a categorical at 2 levels, a categorical at 3 levels, a categorical at 5 levels, a categorical at 7 levels. So, maybe this is closer to what a lot of people testing systems are. I've got these kinds of aircraft with these kinds of sensing systems with these type of weapons, with these, in other words, there are all kind of categorical combinations that you could have. And just to, again, show you, I can save these factors. So if I want to make this same design again, I'll have that handy. So if I make this design, you'll notice it didn't give me even the choice of the classic fractional factorials or Plackett-Berman. It also didn't give me the choice of orthogonal mixed level. The only thing that makes sense is to run a design like this. So if I pick, say, 35 runs here, why am I picking 35? Notice it's going to be divisible by 7 and divisible by 5 evenly there. So I'll make that design. We get a little rest. Okay. And I'll just make the table for this. And you can often see what the structure is by looking at the top, but the other way to do that is to actually make the distributions, put the factors in, ask for the histograms only. And now you can see that it's as balanced as it could be. Okay? Now, I say that 5 and 7 levels both divide into 35 evenly, but 3 goes into 35, and I can also turn on the for these histograms, show me the count for each one. You'll notice you get 11 for level 3, but 12 for level 2 and level 1. Okay, so to me this is a better design than if I go back out to just show the last point here. So here are these factors waiting to be loaded. I go to custom design, I load those factors in so you don't have to watch me type it in. But if I ask for a 35 run custom design, this is going to be a de-optimal design, and it would work fine. So if if the only thing you use is the custom designer for most of your work, you're going to get workable designs. The only thing is when we make this one, and again, I'll make that same distribution and turn on the number of counts. It's not quite as nicely balanced. That's really the difference. So if you just use custom design, you'll be fine. But if you're someone that does lots of categorical factors, with some frequency, knowing about the orthogonal and nearly orthogonal design would be of use to you. And Brad, I'll open it up to you, and it gets to be your turn if you have any other comments on the newer screening designs that have come about in recent times. All right, that was very quick to do modern screening. Closing up some things. We're going to very quickly talk about efficient modeling and simulation. So there we are, almost back to probably a way to clean house quicker than that. Okay. So there's a entire slide deck on this available. It's full of references to all sorts of examples. There's even, so the Military Operations Research Society, there's basically a recording of me doing almost this whole tutorial there. There's also a recording from a Jump Discovery Summit of Jim Wisnowski doing a example of jump in beast mode. They built an add-in that does boundary exploration through adaptive sampling techniques. Don't have time for them here, but the links are going to be in the slides. Okay, scooting ahead here. When I worked for the Army, which is now over 15 years ago, I worked on a modeling, simulation, and analysis team at the Chemical Biological Center. So we would frequently look at sort of physics-based models of transport and dispersion of agent clouds. That therefore we could do simulation testing of detectors, or look at what would be the dosage level from an event, and therefore what would we have to do from a decontamination point of view. And the point is, back then these simulations seemed to take a long time. It's 15 years later, computers are a lot faster. Guess what? We just make the simulations harder. We still have simulations that can take the better part of a day. So what we're hoping to do is run a small number of simulations and build a fast surrogate model with which we can now make predictions about our processes. So there's really sort of three types of simulations that I ran into. The complex science-based, like the CFD I just showed, but then you'll also see a lot of agent-based models and discrete event simulation models. These are often can be modeled with simpler, low-order polynomial models, but they can be stochastic, so we're often more interested in understanding the variability in those systems. And so, example, if anybody's ever done any type of red-blue force simulation, if you only run it once, either red or blue wins, and that doesn't tell you a lot. But if you run it 100 times, and red wins 52 and blue 48, well, you're getting some idea who's got the edge. And it might be 70-30 as well. And then discrete event simulation, think of this more like a lot of people down at Georgia Tech Aerospace System Design Lab look at problems where, what's the most efficient way to load a ship or aircraft, not just in time, the volume of material you can get on. And again, that's looking at a lot of stochastic behavior. So those are the types of designs or simulations we frequently run into. I do want to point out that JMP has built into that prediction profiler we've been showing you all day is an actual Monte Carlo simulator where if you have knowledge of the variability on the inputs, so down below here you can see I've got the 4 bell-shaped distributions. They don't have to be just normal distributions. There's about 15 different types. It can even be sampled from a data table where this is just historically, we've done this, for years. If you just randomly draw from that data, you can mimic the variability on the input. Then there's sort of two big assumptions. One, we've got a good idea of what the variability is on the input, and if we've got a good model, a good relationship between what we're trying to predict and the x's, then we can sort of transmit that variation through the model. So over on the right, you see a couple of distributions here. And right now, they're well outside the spec limit. So you can see the defect rate circled in red is up around almost 100%. So I'm just going to turn on this animation here. And as I move the process, you can see that the defect rates are going to begin to drop as I move the process into the spec limits. But at some point, I'm not going to be able to ever get the top distribution other than it being centered within the spec limits. There's always going to be some leakage of the tails outside of it. I'm always going to have a certain amount of defect rate there. The bottom distribution is sufficiently above that I'm really in the clear there. Well, this is where now you're quantifying that uncertainty in the process, and you can start to have a conversation about how much maybe can I move the rate up, because maybe that's hurting, the speed with which we're producing this result, and still keep my defect rate low. Okay, so recognize that you can add this stochastic behavior to some of your deterministic simulations. Okay. There are sort of two classes of designs we use. The one group I'll call traditional, but you can see the long list of names there. So factorial, RSM, orthogonal array, definitive screening designs. These work well with the low-order polynomial simulations. And then I have down below it the space-filling designs, which are often used with more deterministic simulations, so more of the physics-based. And they're often modeled with what it's called Gaussian process or Kriging modeling. Think of that more like an interpolation technique that connects the dots as the approximation method rather than a regression, okay? And this is, if you had to sort of picture the difference between these two types of designs, the one on the left here is that same central composite design that's been featured in several slides here. We've got all the corners, middles of the faces, and the center, but really for every factor, there's only a low, a middle, and a high, which is great if you've got a low-order polynomial. But if you've got a process that falls off a cliff or has a spike somewhere in the middle, you might not have data near it unless it fell near the 50% of the range. So the design on the right, and I put all sorts of drop lines there and put all sorts of grid lines to show you, is a 17-run Latin hypercube design where in every factor, if you follow the drop lines, there's one at 1, one at 2, 3, 4, all the way up to 17. So there's basically 17 baby steps in every dimension. And that way, if you have a process that falls off a cliff or has a spike, you have a much better chance of modeling that with that type of design. So I think at this point, I'm going to skip right through this sequential design conversation. Maybe just make a couple designs and yeah, let's do that. And if there's time, I'll try to open up this one example from of a helicopter simulation flying surveillance where we look at some factors. Okay. Again, on the clock, I've only got a couple minutes left. So let's just make a, so here's a, yeah, let me not do that one. I'll start with a simple one here. So here's a three-factor design, and I've got the ranges here. So if I go into DOE, and under special purpose, we're going to go to space filling designs. You notice if I hover there, it says, creates a design for a system that is deterministic, no variation, or near deterministic. So if I come in here, I'll load the factors. And by default, it's going to do 30 runs. Okay, if I wanted to, I could add constraints. We've seen that before. But there are multiple choices here for different types of designs. Let's just say that most people doing this are going to be familiar with Latin hypercube design. I'm curious, anybody in the room ever used a Latin hypercube? So we're getting about a fourth of the room. So what we're going to see in JMP is we have one that's pretty unique here called fast flexible filling. And so I'll do a little work with that as well. But the reason for this default of 30 is just, it's sort of in this field, people are looking to run typically about 10 runs per active factor. So if you have 3 factors, you start out thinking, I want to run 30. But what if we had 10 factors? We're probably going to want to run 100. Now, if you got a really long-running simulation, you start thinking, maybe I could run 30, see how well I'm doing, and augment that, do another round, see how well I'm doing, augment that, kind of do it sequentially. So I'll just make the Latin hypercube first here. There is the design, and I'll make the table for it. And you notice all the decimal places? Okay, I'm going to go back. I'm going to change this to, the number is 33. And this is just having done this, when I worked for the Army, by picking one more than 2 to the number of factors, or 2 to some power here, notice I get nicely spaced settings on my factors 1 and 2, so nice round decimal places. Whereas the third one is got a lot more decimal places on it. I don't know if that's obvious to you there, but here's the resulting design. Okay, and so there's a 33 trial design. If I had done a 17 trial design, I would have had all integers for variable x1 because I had a range of 1 to 17. Okay, what does that design look like? A good way to look is with when you have just 3 dimensions here, is put it all in. Okay, and I'm going to make those points bigger. And so in some respects, it looks kind of like a shotgun blast, okay? But there is, if it is a Latin hypercube, 17 baby steps, or in this case 33 steps in each dimension. Okay. Let's make this a bigger problem, and let's throw in just a couple more things, and this will be maybe my last design. But let's make this again, a space filling design, and we're going to put in 10 factors. And we'll put in 10 that are continuous, and maybe we'll put in 1 categorical at 5 levels, okay? So this is a simulation, but I'm going to do 5 different types of aircraft, for example. That's why I've got that categorical factor in it. So when I go to continue, you're going to see that the choices are now down to just fast flexible filling, because these other methods don't support categorical factors. For that matter, they also don't support constraints. So if you remember we did time and temperature constraints on my pizza problem. Well, here maybe I want to also throw in a constraint on factors 1 and 2 here. I want to sort of lop off the upper right-hand corner of their design space. So I'm going to say their sum has to be less than or equal to 1. So everybody else has a 0, so they're not in the constraint. So this design is going to be space filling, but it's going to have runs. We're going to have constraints on x1 and x2, and we're going to have categorical factors in it. So we'll just hit fast flexible filling. And what it's done is throw out 10,000 points into that 11-dimensional space and cluster them to be roughly equidistant from each other. And so here's the table, but if we wanted to look at this design, we could either look at, say, the scatter plot matrix. And what you'll see is, in particular, that upper right one, notice that kind of right corner clipped off because I said don't go to high combinations of x1 and x2. And then down below in the bottom row, I'm going to turn off the jittering. Jittering lets us see points that sit on top of each other. And now you can see there are just 5 rows of data there because we've got our 5 categorical levels. So I think in the interest of time, I'm going to pause and we'll start the conversation with Brad Jones. But I do want to point out, and the slide deck reflects this, you can augment designs, space filling designs, you can put constraints into them. So if you are doing computer simulations, particularly the longer they are, the more interested you're going to be in, can I do that sequentially? So you get to a point where you know, I now have enough information, we're not really getting anything new by doing any more simulations. That's a good time to stop and particularly free up that high performance computing for other folks to use. So that was kind of a quick, roughly 35 minutes of modern screening and space filling designs, but we're here all week, so please corner Jim or myself. And are you hosting this part up with Brad or reading him questions?
Well,
or?
you know, I thought maybe you could just start off with kind of the less technical. I think you guys have had a really good
So-
fire hose.
So maybe if you want to bring Brad up on the screen, and I'll unplug, or I'll just stay plugged in case I need to
Yeah.
show something. There he is. Welcome,
Yes.
Brad.
So hopefully you can hear.
Good to be here.
I thought maybe we could all kind of come up for air after they've got this massive dose of technical information, so you could just kind of talk about the current state and maybe some future directions of research, and then I know we have specific questions where, you know, maybe you want to pull up, a few different, whether it's some slides or pull up jump and figure that out. But maybe you just want to start out with a little bit of, you know, here's what you're seeing as some of the exciting things going forward and whatnot.
There's a question. What did you want me to talk about, Uzo?
Yeah, so if you could maybe comment on what you see as maybe our current state of DOE and maybe some of the future research directions that are promising that that could solve a lot of problems that we're seeing across different industries, but obviously more so in the NASA DoD sector.
And maybe Brad, if I could make it more specific, you know, I breezed past like orthogonal mixed level. It's something, you know, that's just come out. Maybe address the screening side of things, and then if you've got anything in the computer simulation area that you might want to add. I think those were topics that people here were interested in.
Okay, well, it's good to join you. I think that there are a lot of new stuff going on in DOE. 30 years ago, you couldn't get an NSF grant in design of experiments because the reviewers of all these grants thought that everything that was knowable about design experiments had already been found out. And that has really changed in the last 30 years, primarily because of the power of computing. And for instance, the fast flexible filling design, triple F, those designs involve a lot of computing behind the scenes that makes it possible to do what Tom was talking about in his last example, where he cut off part of the space of two factors, and then he also included a categorical factor. There haven't been any other sort of traditional kinds of space filling designs that could do that sort of thing before. In terms of what I think, looking in my crystal ball about the future, one area that I think needs a lot of attention is design for continuous processes, so that sometimes when you're running a process, things are happening during the process that you might want to, where you might want to change things as you were going. And designing in those cases becomes more problematic, and there needs to be some actual new capabilities there. So anybody who wants to work on that kind of thing, they would be making a big contribution if they did that, if they found something really useful. I have been doing a couple of things that are new that might be interesting to you. One thing has to do with again, triple F designs tend to fill up the space of the factors in a kind of uniform way, and that would make it possible to do the kinds of things that are usually done in fitting space filling designs, like fitting Gaussian processes. But especially in the case like what Tom showed, it might turn out that a Gaussian process would not fit the data very well. So it'd be nice if you could have a compromise between space fillingness and optimality. And that's been a topic of research that I've been working on. I could give a quick demonstration of that if interested. Interest?
Yeah, I think there is, because a lot of ModSim folks here. And we did make the mention that, hey, one hybrid type design is to come up with your optimal design first and then augment it with space filling. So now your approach is to do a one-shot that kind of will take into account everything all at once.
Yeah.
Yeah.
So let me share my screen. And so you can see my copy of Jump up there. Yes?
We're there.
Okay. So what I'm going to do to start is create a space filling design, and it's going to be a triple F design. And I'll just do it for two factors, but I'm going to do it with 100 runs to start out with. So here's my table. And now I'm not suggesting that you run this design, but when we look at this design in a scatter plot matrix sort of way, you can see that it's really covering the space in a very uniform way. But from the standpoint of optimality, that 100 runs is not going to be a very good design in terms of D optimality or A optimality or any other kind of variance kind of optimality. So what I'm proposing is this. I'm going to add covariate factors. So I'm going to make X1 and X2 covariates. And I'm going to, instead of using all of them, suppose that I only do 20 of them. And let's say that I want to be able to fit two-factor interactions and quadratic effects. So now what this is going to do, let's say I'm willing to do 20 runs as you would with a regular space filling design. And so I'm going to do that. And normally in a problem like this, if you just use the custom designer, you would get de-efficiencies in the 40% range. Here, we've gotten de-efficiencies in the almost 40%, but here, if I look at a graph of that's not what I wanted to do. Here. I need to do it with my 20-run design, not my 100-run design. So here's a 20-run design. I have to make the table. So now I've made a table that's only taken a fifth of the runs of the original design. And so I'm going to do the scatter plot matrix. And we can see now that we have a design that's not uniformly space filling, but it has a whole lot of levels of both factors, and at the same time, though, it's quite efficient from a variance standpoint. And so it's accomplishing a lot of space fillingness at the same time as it's getting very high efficiency for fitting a full quadratic model. So this is a compromise kind of design. As you add more and more runs, you get more and more space fillingness. But this is the kind of thing that you could do when you want to have an off-ramp from the normal way that people often do the analysis of space filling design using Gaussian processes or neural nets, for instance. This would support very well a full quadratic model. And it would allow you to look at more complex functions because you have a lot more levels. So this is just an idea of a new thing that hasn't been proposed before, as far as I know. There are some questions I know that you've asked, so you want to clue me in on those?
We started out the day showing an example of how a log linear variance model in the analysis piece works and how it effectively changes your confidence intervals where you have the high variance type activity. And there was a question that said, that's neat. I might like to use some log linear variance analysis methods, but what do I do in the design phase to set myself up well to estimate both a mean model and a variance model?
So in your example, did you replicate points in the design?
We did both. Actually, I don't think I showed the one where we just used center points. So you can do the log linear variance with just centers, but yes, there were replicates in ours.
Yeah, so I mean, you would do maybe different things when when you either have to do a one-shot experiment or if you could do things sequentially. If you're going to do one shot, then you want to do replicates of most of, or if not all of the design points, so that you get reasonable estimates of the variance across the region of experimentation. But then, if you were able to do sequential exploration, once you have a model, a log linear model, you would have areas where the variance was larger and areas where the variance is smaller. It might be that you want to do better in the region where the variance is small. And that would be lucky, because then you would have more control over what's going on in that region. But in the case where you are looking where the variance is large, you would instead want to do more runs in that area. So you would change the ranges of the factors so you were in the area that you wanted to be in, and then you would need to do more replication in order to get a better job. But there's a kind of another way you can do this sort of thing that's maybe not as fancy as log linear variance modeling, but it's also can be a little bit more practical, I think. And that is you create a second response, which is the variance for each factor setting, and then you model both the mean and the variance. In fact, it would probably be better to, instead of modeling the variance, model the standard deviation, because that's going to be more like a normally distributed variable than the variance is. So if you model both the mean and the standard deviation, you would again get a feeling about what how the standard deviation is changing across the region of the factors, and again the profiling would work, and you would have you'd have something that perhaps would be easier to explain to management. I'm not advocating for not doing log linear models. I'm saying, well, it's always when you have two ways of doing things, do both of them and find out how that how different are they, and can you get more intuition out of one or more prediction out of the other? Does that make sense?
It does. So it's more on your strategy in attacking it from an analytic perspective versus something in the information matrix or some optimality criterion that you would kind of focus in on, right?
Right. Well, exactly. And this second approach that I'm talking about, where you separately fit the mean and the variance, this would be much more likely to be have some optimality, some that you could argue, because both variables would be more likely to be normally distributed, and so the usual optimality arguments for the design would hold better.
Okay, so similar question is, if you know up front that you have some random effects for your factors, so not necessarily split plot only, but we're just going to say we have some random effects, are there designs that take that into account?
Yeah, actually, the design group at JMP is working on, as we speak, a more general approach to making designs for more than two variance components. If you do a split plot design, you have the random error variance, and then you have the variance of the plots. But you can cheat a little bit. You can have a design with two random effects other than the error variance by setting up a split plot design, but not not asking for the effect of the whole plot, the main effect of the whole plot variable. And then it would, that would create a two random effect model. But the other thing about it is, if you just, in JMP, if you go to the custom designer and say, you have some number of factors, and you say, I want to group my runs into random blocks of size 4. Now you're going to get a designed experiment where you have random blocks of size 4. So you get this design here. You get 3 blocks of size 4, and the analysis of this would give you random, would take into account that you have not only the error variance but the random block. But for instance, suppose that you wanted to add maybe instead of doing just this, I didn't want to do that either. I hate that part of Windows. Let me back up. And let's suppose I add a categorical factor with 4 levels to this. And so I'm going to make a design now with 16 runs, so it's a multiple of 4. Oh, and I wanted a random block while I was at it. I'm also going to have random blocks of size 4. So I could make, when I could simulate data from this. And I could make this, in the analysis, I could make this factor be random. So it'd be like a random categorical factor. And you can do that by assigning, right now we have the random block, but we can also make this guy be random too. So now we have two random effects, and we can fit that model. So that even though it wasn't designed to have 2 random effects, that wasn't a part of the design. You can, after the fact, make JMP analyze the data as if there are 2 or 3 or 4 random effects. So that might make things you can use that sort of in an ad hoc way to get what you want, even though JMP doesn't support multiple random effects. Does that help at all?
Yeah. Makes sense. At least part of the way there, but I can see why Team Jump and Carrie is working on that a little bit more. So,
Yeah, it's a complicated problem for two reasons. One is that there's a user interface issue. You might have a split strip plot, where some of the variables are nested and some of the variables are crossed, and things can get really complicated there. And the problem is trying to come up with a user interface that's where it would be obvious how the units and the physical units are going to be allocated to the various blocks. And so there's a UI problem, and then there's the design problem, which is also difficult. So that's been on the list of things that we would really like to be able to do for multiple design cycles. Of course, I shouldn't say we because I no longer work at JMP, but I still sort of identify with it. I'm retired from JMP, so. But there's a good team there. They're smart people, and they're really doing every design cycle, they get amazing amounts of stuff done. Like, for instance, this design cycle, they got 2 different mixed level design capabilities added to JMP.
So last one from me is an easy one, probably. So we're doing a split plot design, and let's say temperature is the hard to change, and then we have whatever 3 other easy to change. And I have 4 blocks, and I generate the design, and lo and behold, it turns out, due to randomness, that I've got, and temperatures high and low. So the first 4 runs are going to be low, and then the next 8 runs, so actually 2 whole plots in a row, are going to be high, and then the last one is going to be low. So I got lucky where I really only have to change this twice. So the question is, does it make sense that we want to kind of force it to change every block we should alternate? Or can we, and I made the comment, and Tom rightly corrected me, that you really probably don't want to do that. I said, hey, you can just say you got lucky and you don't have to change it but once or twice. So maybe your thoughts on that.
Okay, temperature I want to be hard to change. And I'm going to do 4 whole plots, so I make the design. And I don't know if the same thing will happen where you get 2 in a row of the same. Right, so this happened.
Right.
So
We were fortunate.
yeah, or unfortunate, as the case might be.
Exactly.
One thing you could do is force whole plot 4 to go after whole plot 2, so that you're going minus to plus to minus to plus. The idea of just keeping this one constant for 6 run is not a terrible idea. But if you do that, then you should make the whole plot be, you should do this. Because really, you don't have 4 whole plots, you only have 3.
That's a good point.
Do you see what I mean?
Yeah, for sure.
The whole point of split plot designs is that you're going that when you change the hard to change factor, 2 things happen. One, the fixed effect of changing the factor happens, but the other thing that happens is that there's a kind of a random kick to the process from changing the hard to change factor. It's actually, if there wasn't a random kick, then you could just ignore the fact that you had run a split plot design. You could treat it as if it were a completely randomized design. But you don't know whether the whole plot variance is going to be 0 or not in advance of experimentation. So it's a dangerous game to pretend that your whole plot variable isn't actually doesn't really have a random effect associated with it. But this is the way to actually, if you were going to do it that way, you would need to only since you're not going to vary this for 6 runs instead of 3, you should tell the truth to the analysis procedure, and just so you would have 3 whole plots that would be different sizes.
Which then is definitely going to influence your power. So if you have the ability up front, you should force it to alternate so that
Yeah.
you can maintain the power.
But from a logistical standpoint, you might like the fact that you only have to change things 3 times instead of 4 times.
It's the trade space. Nice.
Brad, we have one more question here from the audience. How should we incorporate Bayesian stopping rules into a DOE run plan?
You have to tell me more about what you mean by Bayesian stopping rules.
Is the questioner here? Yes, he is. Maybe I'll take him the microphone so he can explain. But while I'm walking there, I'll comment. It sounded like I'm going along with my DOE and I'm analyzing and, ooh, I think I can stop.
That's a good summary. The idea is that if we had a run of 30 tests planned and we're continuously updating our expectation and the probability of what we're seeing, is there a case to be made for stopping early under traditional DOE?
Absolutely. If you're updating your response data as you go, and you have and you've gotten to the point where you believe your model is a strong one, then there's no reason that you have to complete the design. I call that the boss option. You're the boss, not the design, not the software. So you could, if you're taking a Bayesian approach, and you could use stopping rules that had to do with the posterior distribution of your model. So and once your posterior distribution got sufficiently narrow, you could stop. Did I answer your question?
Thumbs up.
Okay.
If I could ask, following on, I feel like that is an approach that works well in computer simulation, because you tend to be able to generate these runs and continually look at how your surrogate model is doing, and if you compare that to some test points, at some point your surrogate model is suitably accurate that you say this is a good time to stop. But if it's more of a traditional real world test DOE, and you've proposed a response surface model, say in 5 factors, there aren't that many degrees of freedom that you almost have to run the whole design before you can fit the proposed model. All you can fit ahead of time are simpler models. And I suppose if the simpler models are working, stopping makes sense, but if you can't fit the full model until you're 80% done, you haven't gained that much.
Yeah. that might be an argument for not doing the full, not even thinking about doing the full response surface design at the beginning, but instead doing a smaller design like a definitive screening design with fewer runs, where you have the possibility of being able to fit the full quadratic model even in a smaller number of factors. And then if you don't turn out to be lucky in that sense, it still might be the case that the augmentation that would get you the model that you need would still be smaller than the RSM model was to begin with. And that's especially true in situations where there are more than 5 or 6 factors, because the RSM models start getting, especially the classical ones, start getting really expensive in terms of the number of runs.
Well, and Brad, we actually kind of demoed that exact situation. I had the CO2 data where we did a definitive screening design, and it's sort of a slam dunk that 3 of the factors very clearly had an effect. And it was sort of, depending how you did the analysis, there were 3 others that were sort of on the edge. And so I augmented that original 24 trial design in the 6 factors to support the full response surface, and it was only 12 more trials. And the point is, if you knew the right 6 to start with, the optimal design was only 34. So it kind of showed that idea of the advantage of using a definitive screening design, and if you're not lucky enough, the augmentation was inexpensive.
Yeah. Which, I mean, I think that people have fallen away from the idea of sequential experimentation and have been wanting to do one-shot experiments. And there are times when you don't have any choice. Like if you have production equipment, you may not get back onto that production line anytime soon. So you best get everything you need in one shot. But at the same time, it's almost never the case that you need all the terms in a full quadratic model to get a good fit. So running the full quadratic model, the design for the full quadratic model seems wasteful, and you can get away with if you have some notion of how many effects you think might actually be necessary, you can get away with doing much smaller designs and using Bayesian de-optimality to choose your runs. I guess I could give you an example.
All right.
So,
Brad, hang on just a second. It looks like we've got 5 minutes left. I do want to turn to the audience and ask if, in the conversation with Brad, if any other questions have arisen with anyone. You're more than welcome to take the mic or relay the question to us, and we'll ask him. Okay, we're not seeing any more questions coming from the audience, so I guess if you want to either give an example or a final comments.
Let me just do this one quickly. So I'm going to have a 6-factor design. If I wanted to fit an RSM, I would have to do 34 runs here. But I could say instead, all these effects are only if possible. So I'm going to require that I be able to estimate my main effects, but all of the second order effects I'm going to say are if possible. And then let's say I'm willing to do, instead of 34 runs, maybe I'm willing to do 20 runs. So now it's going to make sure that I can fit all the main effects, but it's going to do as well as it possibly can at being able to fit the two-factor interactions and quadratic effects. And so this kind of design would be another way to approach that kind of a problem that would save you in terms of resources.
And Brad, if you're unlucky, this can always be augmented.
Absolutely. If it turns out that you need more effects, you can augment this using the augment designer and jump, and with whatever you follow-on model do you think is necessary. But you can use the rule of thumb that if n is 20, then I can handle up to 10 effects. And identify pretty much any 10 of the effects. So there's kind of a cutoff in design of experiments where when the model has more terms than half the runs, you're in trouble in terms of both in terms of model selection and also in terms of interpretability.
Well, I do think the example you just gave with I don't think we show it enough to people, but where he turned the model from necessary to if possible, that's been there for more than 10 years for sure. And so the person who had the Bayesian question, I hope this gives you an idea of an alternative path to how you set up that sequence of runs. Well, all right. If there are no other questions, let's thank Brad for joining us.
Thank you. I enjoyed talking to you. I'm sorry I can't be there.
And again, I will remind you that Jim and I are here for the rest of the week. So if there's anything we didn't get to, which is a lot, covering arrays, functional data, I don't know the rest of the list, but all of the content that we sent you that was online, please take a look. There's going to be at least, I have a 4-page Word document full of links to various videos on topics. So many of the topics we didn't get to, you'll be able to download that. And if you have any question on anything, please send us an email. I think our contact information is around, and we'll be sure to follow up with you. So thank you very much for attending our short course, and we look forward to talking to you this week.